The session is Eliise Tammekivi from the Institute of Analytical Science that will be speaking about offline LC SFC-HRMS method for non-targeted analysis of depolymerized linen.
Thank you. Hello, everyone. As it was said, my name is Eliise, and right now I'm a postdoc in the Institute of Analytical Sciences in the University of Lyon in France. And just today I'm going to talk about an online 2D LC method that has shown great potential for the non-target analysis of depolymerized lignin. Oops. Okay. So first of all, what is lignin? Lignin is mainly obtained as a byproduct of the paper industry, because when we take wood, we first have to separate lignin from cellulose, because otherwise, if we make paper out of cellulose, it would be very yellow and rigid, and this we don't want. So we have to separate lignin. However, it's approximately 25% of this biomass, and right now it's considered as a waste, and only 2% of it is commercialized. But in the name of circular economy, we want to valorize it, of course, more, because we could isolate some chemicals out of it, for example, or we could also convert it into biofuels, or we could also produce some novel biomaterials. But all these processes need to have structural characterization of this material to have these processes as efficient as possible. But we need to analyze the final product, or then, for example, the intermediate depolymerized lignin. However, this is quite a complicated task, because the depolymerized lignin is a complex mixture, as it consists of numerous different compounds, but also at the same time compounds that can be structurally very similar, including isomers. And these compounds there are mostly neutral. Therefore, we thought that the possible solution could be two-dimensional chromatography, where we combine RPLC to SFC. So SFC has been mentioned a few times, yesterday mostly. SFC is the supercritical fluid chromatography that we can use basically as a normal phase chromatography. So if we combine it with RPLC, we can have orthogonal separation. The other issue is that there aren't a lot of commercial standards available. So for monomers, so those compounds just that have one aromatic ring, there are quite a few commercial standards available. But for dimers, so those compounds that have two aromatic rings, it's more complex, because there are mostly just a few dimers commercially available. So we thought that the possible solution here could be non-target analysis, combining high-resolution MS together with the fragmentation to get more information about the structures of these compounds. In this work, we use the 2D as an offline method. So this means that we do the first LC separation, we collect the fractions, and then inject them into the second dimension. Of course, compared to online 2D, it has its pros and cons. For example, it's good that we can now dissolve the fractions in a solvent that is more suitable for the second dimension. It's also easier to obtain good quality MS2 data, because this is a LC method. So first, when we do the MS, we first have to do MS1 and then do the fragmentation to get the MS2 data. So if we do it online, then the second dimension, it's independent of the time of the first dimension, and we can do it a little bit longer to get the good quality MS2 data. Also, we don't need any complex online LC SFC system, because right now it's commercially unavailable. But my colleague Marco Sanchez will present this topic more in detail tomorrow. So this will be for tomorrow. However, doing this method offline has its disadvantages. For example, it's quite long. As I said, the second dimension is a little bit longer, and we do it offline. So yes, it's longer. And there's also a higher risk of contamination, because we collect the fractions and inject them to the second dimension. It isn't done automatically. First, what we did then was that we used the 33 monomer standards that are often found in lignin, because we used them to find suitable columns for the two dimensions. So we wanted to see which of these, we screened a lot of columns, and we wanted to see which of them had the best selectivity or separation for these compounds. And we saw that for the RPLC, the Kinetics F5 had the best separation, and for SFC, it's the Taurus 1AA column that had the best separation. And it's not a very big surprise because both of them are known to be able to separate compounds that are aromatic and also have OH groups. So it's very suitable for our lignin compounds, which are largely phenolic compounds. And then we use the real-life depolarized lignin sample to now optimize the two separations separately. We just used the RPLC UV and the SFC UV to make sure that everything elutes and everything is good. And you can already see here that the profile is totally different. So this already shows that maybe they are suitable for the 2D separation. And the 33 monomer standards were also good because now we could use them to study the separation mechanism more in detail. So on this plot, it's a 2D plot, and all of those points there are the monomer standards. And we could see that the separation depended on the number of double bonds. So the more there were double bonds in the structure of the monomer, the more retained they were on the SFC dimension. Also, the location of the double bond had an effect. So we could also separate this way isomers. Another thing that was very important was the number of OH groups, because the more there were OH groups, the more retained those compounds were on the SFC dimension. And this effect was so important in the SFC that we could even section the whole 2D plot based on the number of OH that was in the structure of these monomers. And also it was important how hidden the OH group is. So if it was more accessible for the SFC, then it was more retained on the SFC column. And a lot of these interactions were also seen on the RPLC dimension. But one thing that was with RPLC, but we didn't see with SFC, was that in RPLC also the hydrophobicity has an effect. So this additionally now helped to separate some compounds that wouldn't be separated in the SFC dimension. Then we use the depolarized lignin sample now with the whole 2D method with the MS detection. And we could see that, as expected, we got a quite high peak capacity. And as I said before, the analysis time was quite long. But we could see that there is a good separation of the depolarized lignin compounds. And what we were especially interested was the separation of isomers. And for example, here, these are isomers. So there are two peaks, 1 and 2, that would co-elute if we would just use the LC. And we could see, indeed, if we look at the MS1 now for these two peaks, we can see it's just one mass. So if they would co-elute, we wouldn't even think that there could be isomers. But thanks to this method, we could also get nice MS2 spectra. And here you can clearly see that those are quite different compounds, still isomers, but have different fragmentation. So because of that we can have good MS1 and MS2 spectra, we decided to use a software called MS-Dial, which can use to do the peak picking and also some MS deconvolution. And using that, we could see that there are 471 potential lignin compounds having the dB value over 4. So dB value, if we have the monomer, then it has one aromatic ring, and then it is at least 4. If it's a dimer with 2 aromatic rings, it is at least 8, and for trimers, 12, and so on. So we have the dB value ranges, and now if we use those, we plotted the same data using the dB values, and we can see that there appears to be some classification based on the dB value. So now this is good for comparing different samples to each other, because we don't even need to do any fragmentation for this, because the dB value just uses exact mass, where you get the formula to calculate the dB value. But we wanted to get still more information about the structures. And one thing is that we can do the annotation based on 4 criteria. We have the retention times, the accurate mass, and the fragmentation data. And for example, we can use the same monomer standards. So the monomer standards are in red, and the blue are the monomers from now the real-life sample, and we can now just see if we can detect any of them in the sample. And we did. We already could see 2 of the lignin monomer standards, but we wanted to get even more information. We wanted to know what are the other things. So, of course, for that, now we had to look more into the fragmentation results. And one way to look at the fragmentation or MS2 data is to use molecular networks. These are freely available on the GNPS network. So if you want to do it, it's also possible to do it for GC data. And what is molecular network? It's that it connects together compounds that have similar fragmentation pattern. So if they are similar, then they are connected closely to each other. So on this example, on the right, all of the green dots are different compounds that we detected. And if they are connected to each other, then they are structurally similar. In our case, we had to use a feature-based molecular network, which is also available on the same platform. This one just also allows us to show compounds that have the same monoisotopic mass, but different retention time. So it means that we can show compounds that are isomers, because in the classical molecular network, they would be fused into one point, and we couldn't really look at them separately. In our case, yeah, it was very important to use the feature-based molecular network because the sample had a high number of isomers. 77% of the compounds had at least one isomer in the same sample. So this is the same molecular network that we got for our sample. And we now look, or I will show you 2 examples that we saw there. So there's blue isomers and pink isomers. So first, with the blue ones, we could see that there were 3 isomers in this sample, and we can see that the isomer M is directly connected to isomer L, but K is more far. So we thought that, okay, possibly M and L are more similar to each other. And now if we look at them on the 2D plot that I showed before, we can see that compound K is in the area of 1 OH, but the other 2 are in the area of 2 OH groups. And we also next used a software called Sirius. So this is, again, a freely available software that you can use to predict structures based on the fragmentation. And now we could eliminate some of the structures that the software provided. And we could think that possibly compounds L and M are positional isomers, but compound K seems to be something different, but still is an isomer. The other example had 6 isomers, where compound E was more far from these 5 other isomers. And now if we look at them on the 2D plot, we can see that this is an interesting example because it doesn't matter if you would use LC or SFC, some of those compounds would still co-elute. We tried to do even a longer SFC, so it was half an hour SFC, to see if some compounds would separate, but no, still they would co-elute. And now we can see that compounds B, D, and D, for example, they co-eluted, but thanks to the molecular network, we can see that compound B and D are very structurally similar, but there's also compound E that has very low intensity that seems to be structurally something more different. But just to get more information about those compounds, we would need standards, or we would need to analyze the fragmentation spectra more in detail. So with this, we saw that the offline 2D method is an efficient method for the non-target analysis of lignin, because we could do the compound annotation based on 4 criteria. We had a good separation of lignin compounds, including the isomers. And we could also see that there's a grouping of lignin compounds on the 2D plot based on their DBE value. And if you want to know more about this, of course, you can ask me now or later, but also we published these results recently in Analytical Chimica Acta. And with this, I would like to thank my colleagues from the Institute of Analytical Sciences and also all of our collaborators and, of course, you for your attention.